Okay, so we're all good to go. So we are going over the homework. It's October 18th, and we're going over homework 2 in preparation for next Monday's exam. So I'm starting out by looking at problem 5 that you have up here. So with this one, you want to utilize centripetal force, so the force that acts inward. So you have, oh, sorry. You have like some object moving along a circle, and it's centripetal force that's making it act inward. And the equation for that is the mass times the velocity squared over the radius. And so what the question is asking is, you have a car, so let's just say this is a car going around, and you want to see how fast can the car go for, without slipping. So basically, I think if you were to draw this out in a graph, and I'll use 2 colors. So let's say this is, let's see what I want that to be. Let's see. Guess we can say velocity here. So you would have, so the centripetal force would look something like, well, let me use a different color. Let's use, I guess, purple. Why not? So centripetal force would look something like that, because, you have the velocity squared, and it's, with respect to V. And the coefficient, the frictional force has a bound here, let's say. So at this point, the car can be going, at this point when the car starts going this fast, it starts slipping. And the centripetal force is more than the friction can keep up with. So basically, we want to see what this point is. Does that make sense, by the way? It's just kind of a different way of looking at it. So I'll just use blue in this case. So basically, we want to see when is, bless you, when is friction equal to the centripetal force. And so what is the formula for friction? So it's something times something. Okay. Which we usually write as this mu here. Yes. And then, so it's going to be that. Say it again. Yes. So normal force, which I will just notate as Fn. And so the normal force is going to be the mass of this car times gravity. And then centripetal force, we already got that. That's going to be this one. So mv squared over r. So let me make more sense of it. Can you all see this all right? Hopefully so, because it's not really a way I can make it bigger. Okay. And feel free, you don't have to, like I say, feel free to not write down what I'm doing up here, because I'm going to copy this and paste it in a Word document. So feel free to just look up here if you want. All right, so we got mu here. And then, like I say, the normal force is the car's mass times gravity. In this case, conveniently, mass is going to cancel out, which is good because we don't have it here. Mass times velocity squared over r. And then let's go ahead and cancel. Let's see, let's do it in a different color. Cancel this out, cancel this out. Also, let me put this. So this is the coefficient of friction. Okay. Friction. Okay. And let me go ahead and plug in the numbers. So we got the coefficient of friction being this. So we've got 0.70 times 9.8. That's just the one I'm going to use. Bless you. And we're looking for velocity, so I don't really have that. Let me just leave it how it is. For radius, let me do this to kind of save some time. So I'm going to multiply both sides by r just to get rid of this on the bottom. So then r would be 65. And then all I need to do to find velocity is just take the square root of 65 times 0.70 times 9.8. Does anybody happen to have that in their calculator? If not, I can just put it up here. $55.3 is what you're getting? What are you multiplying by?
0.7 times 9.8 square root 21.11.
Yeah, because that's what I'm getting. Let me see.
Human error.
Well, just make sure you show all your work, because that can happen. That. All right. Questions? Meters per second? Well, let's see. Let's take another, hang on. That's kind of a good detour.
So it's given in meters.
Hang on, let me see. Oh, I'm also putting together a little formula sheet. Can you see that? Okay. So I'm just trying to make sure I get all of them. Let's see. Let's go to the... Okay, there we go. Let's just go through the units. Yeah, and I've been really kind of lazy with the units as of late, which I would, when you're taking your test, try not to be, because make sure, for instance, and I think in one of the homework problems this actually comes up, make sure you have, length in meters, time in seconds and stuff like that. Just keep it consistent, or watch your meters. So actually, let's do the problem just with the meters. So let's see. Or with the units, I'm sorry. So we've got the coefficient of friction. So let me see. We've got, So just remind us of what this was. U times mg equals mv squared over r. So let's put this in like a units version. This we don't, it's just kind of a number, so I'm just gonna kind of not do anything with it. So we've got meters times meters per second squared times meters, or equals meters times meters per Well, actually, we don't know what that is. Hang on. Hang on. Okay, so I'm going to leave that how that is, squared. Then you got meters here, right? Because we've got radius of meters. Make sure I'm doing that right. No, mass is in, sorry, mass is in kilometers. Or kilograms. Yeah, I did that all wrong. So kilograms. Kilograms. As it turns out, it doesn't really matter because those cancel out anyway. But this, we needed this to be in newtons. So that's why you have the kilograms times mass per, or meters per second squared. So multiply both sides by meters. Meters. And you get meters. Meters squared second squared. And that equals velocity squared. And so you just take the square root, and then that's meters per second equals velocity. So that's kind of how you know that. Does it kind of make sense what I just did? I just kind of played around with meters, ignoring numbers. So, yeah, and when you're doing testing, because Stephanie actually did suggest this to me, you know, just make sure you pay attention to your units a little more than what I'm doing right here. Since I'm pressed for time, I'm kind of glossing over them. But just make sure you have everything in the standard meters, second, kilograms, because that's the standard, and things like that. So kilograms for weight, meters for length, seconds for time. I think you call those SI units. All right. Okay, so let's take a look at 4. Are we good, by the way? Do I need to put that up? Are we? We're pretty good. Okay. All right. Okay, I'm just going to put the statement of the problem. Let's see. I'll go ahead and put the picture. It's a little smaller though. Okay, so let me copy what I put over here. The free body diagram I drew. We'll put it in this color. Yeah. And you know, you all just let me know if you take any issue with anything that I write up here, or if something doesn't make sense. Because while I want to go through as many problems as possible, I also don't want to rush through problems and have you not understand any of them. Okay, so okay, good. So this is Mas 2, no, Mas 2, Mas 1. Yeah. So you got tension here. Let's see, let's write these slightly different color. We've got tension here. We've got and then what is this angle? I'm sorry, what is this angle? Yes, because, yeah, just really quickly, because this angle is a complement of this one and also of this one. So that's why these two are equal. 37 degrees. And so here we've got the mass. So mass 1 times gravity. And then here, well, let's say really it's this component that I want. Let's do this. Let me write that in a completely different color. So this component that I want is going to be this component of that. And how do I get this component of this part? And so how do I get this here? Well, it's going to be the hypotenuse of the triangle. So M1G times sine or cosine. Which one is it? Well, it's going to be opposite over hypotenuse. So it's going to be the sine of 37 is what this part is. Does that make sense in the diagram? Do I need to rewrite it? That's not what the answer is. Is that good? You know what I mean? Okay, in the diagram, okay. Does that make sense to anybody? Because like I said, I mean, as you saw, I just got it as I was trying to present it up here. So does that make sense to everybody else? All right. All right. So then we'll sum all the forces. Let's see. All right. So basically, let me see. So the acceleration of the system. So I'm going to write what he has here. So what color do I want? Let's go with this one. So for M2, we can write M2G. So that's this part, bless you, minus this part. That goes up there. So apparently, you know, we're considering this to be the downward part. And he actually has it in his diagram, I think. Let me see. So, acceleration acts in that direction. We'll say, actually, let me do this. So acceleration acts in that direction. Okay. Yeah, because let me also draw a free body diagram with just M2, because he has that on there. So we've got tension acting this way, and we've got M2G, G acting that way with acceleration acting in that direction. And so if we solve for well, let me not solve yet. Put the other one. One. We sum all these forces, so we've got by the way, we also have to consider friction in this case. So I have to plug this in somewhere. And only on this box, because this one's just hanging freely. So we've got tension, which is positive in this case since it's acting in an opposite direction as this. Then friction, which is hampering movement. Friction. Or acting in the opposite direction. And so is this component. Question. Okay. Are you sure? Okay. All right, so this. So tension's acting this way. Friction's acting. Okay, so basically I just copied down what he has here. So let me make sure this all makes sense. So tension acts this way. Obviously this acts in the other direction because gravity is pulling it that way. And then it's going this way. Okay, the thing that's confusing me right now is why is friction acting in a different direction as tension? Because the box is sliding down. Oh, no, wait a minute. The box is sliding up, I think.
Yeah, it's sliding.
Okay. So there we go. Okay, so that makes sense. So where do I want to write that? Let's see. Box M1 slides up. So Right. Same direction as T. Okay. Just a little note there. Okay. So we have two systems of equations, and so we just solve them. So let me go ahead and plug in what friction is. Okay, so what he does, and I don't really have room to do it right now, but he sets, let's see, how do I want to put this? So he combines the equations by setting these equal to each other. So he has to solve for t in this one. So let's see. MJ minus G equals T. And then he takes this and places it in there. And that's a minus sign. And so the result of that, and so the result of plugging this in for this and putting friction in the form that, you know, the normal force times the frictional coefficient gets this equation. Gets us, let me see, I'll do this down here. So M2A minus M2G probably should have put that in green. Let me do this. Equals the normal force times mu minus M1 G 37 degrees A. Okay. And then I guess we can take, I'm not going to try to, because since I'm so slow in writing this, I'm going to let you all work this part out. So if you have paper, just work out what this is. So basically you just need to, let me see, divide both sides by M1. And just plug in the numbers. Wait, hang on. No, hang on. I jumped the gun. Because we got A on this side as well. What is it?
Oh, no, because I had looked up a tutor told me another equation, and I see where he derived it from now.
Okay.
It's because you bring the M2A over, and then you take the A out.
Correct. Let me see. No, stop. Yeah, let me bring this. How do I want to do this? Let me bring this. Oops. Bring this. Yes.
You change the A and the G. I think it's going to be M2G minus M2A.
Yeah, because the M2G should be positive. Because that's your total force acting down.
Okay. Yeah, right there. I did it wrong. Again, it's kind of the same problem I had last time. I tried to be fancy and it didn't work. So thank you for catching that. Okay, so let's see. So M2 G minus M2A, and then let me see, where else do I have that? So M2 G minus M2A. So now let me take this over here, which is good because now I don't have to change signs, or I only need to change this sign when I bring it over and it ends up being positive, which is nice. So M2G minus, oops. Minus M1G sine 37 degrees. And on this side, I have M1A plus M2A. And then, you know, of course, I can factor that out and divide both sides. Let's see. Okay, I'm going to do this. Sorry, that's a minus sign, by the way. So when I put this, what I mean is just repeat what's up here. And that equals M1 plus M2 times A. And then I can divide, you know, I'm trying to look for A. There's no A over here. I need to make sure. So then I divide both sides by M1 plus M2. All right. Oh, and by the way, the normal force, let me just write over here what that's going to be. Let's see. That's going to be the cosine here, because it's the force that acts perpendicular to this part. So let me just write over here Fn equals M1G cosine 37. Does anybody need me to explain why cosine and why not sine? Okay. All right, so then you plug in those numbers. And let's see. Has anybody plugged in their calculator? Because I don't know. It takes me forever to write this stuff. Let's see. What is it? 3.25? Yes. Here I get 3.52.
Yeah,
So, but that's, you must have done something right. So that's good. And you know, the numbers are worked out in his solutions. So that's why I'm not writing out everything. I'm kind of writing out a lot of stuff, but not everything. So.
But I think with because there's a lot of people getting different answers, and the book has a different answer. But I think what a lot of people were doing was what you were saying at first, like thinking that it one went the other way.
Oh, okay.
And so I think that solved my confusion.
Okay.
Well, no, but it didn't specify in the thing, so minus two is bigger.
Let me see, is it, so M2 is the heavier one, so it is going to pull this one down. So, yeah, M1 is 4, M2 is 8. So it is going to accelerate this way, and friction is going to act that way. Let's see, it's going to act. Yeah, same direction as this one. Okay. Clear, or any questions, any other questions? All right. No? Okay. So let me copy this and paste. All right, let's see, which one should we do first or next? I guess I might not go over all of 6, but for part C, the answer kind of, or the answer key goes over some of this in detail, but really it's kind of obvious because, okay, if the box is at rest, then the sum of all the forces that are acting on it must be 0. So that's what the answer is for that one. So that one's pretty simple. So just remember, net force on an object that's at rest is 0. Let's see. That's another good one. Let's see. Do you all have any requests? I might go over 3. 3. All right, let's do 3. And then picture. What am I doing? Ooh. Okay. I kind of want to solve this the long way because, and sorry for you all who were in my study group because we already went over this one. But this problem is easy because, you know, we happen to have the same angle formed here, and the springs are the same. But what if they were not the same? That's something that kind of confused me a little bit. And there might be a question like that on the test. And so I don't want, you know, I want you all to kind of know how to solve it more generally. So we'll draw the free body diagram here. So we'll just call this force A or spring A, and then force B for spring B. And then here we've got, so this is going to be 15 newtons. So I don't even have to write the mass times G thing because it's already worked out for me. 15 newtons, bless you. And then let's see, I guess we'll go ahead and just plug it. We'll say, okay, so first of all, and let me ask you this. So we got a spring constant here. What is the force of the spring? Let's see. Say it again. Yeah, let me see. Do we want to say negative? Okay, okay, okay. I see what you're saying. So let me see. So it's not K that's negative, it's the force that's negative. So the distance it travels, let's see. So this we don't know. What do we want to call that? I guess X. That'll be fine. Yes.
Doesn't have how.
From this, let me see. Well, no, because this is just a spring force. It's not kinetic force. You know what I mean? Okay. And actually, I think that confused me at one point because those two formulas look the same. Let me see. So we'll just say this direction is negative. Up is negative. So we'll have 20 times X. Okay. Actually, let me see. Yeah, okay. So then the sum of the forces in the X and the sum of the forces in the Y. We'll do that. This will allow you to, so this is at rest. So of course we set it equal to 0, both of them. And it is at rest, let me see. Yeah, from the rest position, because there have been times that I've assumed that and I ended up wrong. So this allows you to have two systems of equations when you have two different springs if you need that. As it happens, one of these will be able to say that, you know, spring A is equal to spring B, but I just want to go through the whole process. Okay. So here we got 30, right? Here we got 30. So then the component of this, oh, let's see what I want to call this. So let's see. I'm actually going to call this T A and T B. Let's do that instead. Well, but let's label it right first of all. All right, there we go. So for Y, we have this, which so downward is positive. We're deciding. And so we've got 15 minus, we want the part of TA that acts, you know, parallel to this. So that's going to be TA times sine or cosine. Which one is it going to be? Bless you. Which one? Yes. Because we have hypotenuse, this is opposite, that's adjacent. Cosine 30. And then, let's see, TB cosine. And as it happens, this is actually going to look similar. But like I say, if this stretches a little bit more, then okay, well, all you just do is just plug in this new angle here. So I almost want to change the numbers, but then I won't know if I'm really right. But you all kind of see what I'm doing. I'm trying to just make it really general So it's more, kind of flexible. And then here, we'll see that, the tension on A is equal to the tension on B in this case. But this equation will confirm it for us. So we have the X part of TA. Let's go ahead and say, what do we want to say? We'll just say this direction is positive. It doesn't really matter. And so we've got TB sine of 30 minus that's a B, TA sine of 30. Basically cancel each other out and you get 0. So let me see. Whoa. Oh, shoot. Sorry. Why is it doing that? All right, so we got those two. And like I say, just setting these equal. Can we see that these are going to be, let me do this. So, I can cancel this out and cancel that out. So TB minus TA equals 0, and you can see that it's TB is equal to A, or TB is equal to TA. And so they're equal. And so what I can do, let's call TA equal TB equal just, I don't know what I want, S, just because it's easier to write. So then let me plug this in here to FY. Oops. Let's see. So we've got 0 equals 15 equals S cosine 30 plus S cosine 30 I'm sorry, that's how I do that. S is kind of a poor choice. Hang on. F, I guess. Let me see. Pick a letter. C, because I don't want S because it looks like a 5. We'll just do C. All right. And then I'll throw, I'll throw this and this over there. So we've got this is also kind of a bad choice, but we'll just go with it. So 30 plus C cosine 30 equals 15. And I can factor out cosine of 30 and then just divide. Let me do this. Divide everything by cosine of 30. 30. And then I've got 2C on this side and 15 over cosine 30 on on this side. And so if I'm trying to solve for C, then I just divide both sides by 2. So we'll do it this way. And then that should be the answer. Yeah, so there we go. Which is about, do you happen to have this in your calculator? If not, I'll just put the answer up here. All right, there we go. Good. All right, so that's what I'm going to do on that one. There's another part, but it's worked out in here. So how are we doing? Is this good? Should I go over more? Or, well, is this good? Is it too slow? Kinda. Okay.
So like, you know how you're recording it?
Uh-huh.
It's gonna show up like backwards on the screen. You know what I mean?
Oh, it's showing this part. I checked.
Oh, okay.
Yeah. So, and I think it automatically reverses that because
Oh,
yeah.
okay.
Yeah.
Show the reverse stuff.
Yeah. Well, thank you. Okay, let's see. At this point, I guess I'll take a request from you all. Is there any problem that I haven't gone over that you all want to go over? Which one? Okay, which is that one? Oh, okay. All right. Yeah, well, you don't know because I said don't do it. So, because it was confusing. All right, let me copy this. And what we did is, so in my study session last week, what we just did was just kind of take the formulas that we know, try to transform them into what we want, and then see what it gets us. And as it turned out, it got the same numbers that the professor got for us, but I was uneasy because those numbers did not match the ones in the back of the book. And so that's why I said, okay, let's just forget that. But let me show you how he does it. So like I say, let me see. Just kind of know your formulas, and that can sometimes help you figure out what you're trying to look for. So let's copy. So we got 7 here. And before I move on, let me just save this really quickly. All right. And I'm just making sure I'm just paranoid. Okay, good. So select all that, get rid of it. Okay. All right. So we're trying to find minimum power, and we're also trying to find force. So, well, what do we know about force? We know that force is equal to mass times acceleration. And this, by the way, doesn't always work, but if you see a problem on the exam and you're kind of clueless as to what to do, pull out the formulas and just manipulate them to get you what you want based on what you're given. Okay, let's see. So we want constant velocity based on, so we've got a constant velocity. We need a force. What is acceleration? No. It is mass times, acceleration, is velocity over time. And then let's see. So we've got a constant speed. Okay, that's good. Let's see, we've got all right, so we got 10 kilograms. So I don't know, let's just plug in things and see what happens. Or hang on, let me manipulate this a little bit. Because we have 10 weight over time, that's what that is. So let me redistribute mass over time times velocity. And as it turns out, we happen to have those two, so let's just plug in and see what happens. So we've got, let's bring this over here. Let's see, 10 kilograms per second. I'm going to try to be careful with units here. We've got 2 meters per second. So we've got kilograms times meters times seconds squared. So that's going to give you a force, which it should. And so that's going to be 20, I'll just write it out here, kilogram meters over second squared, which is equal to 20 newtons. And that's what he has here. Like I say, the back of the book has 10, and then when you plug in, so it has 10, and then for the other answer, his answer, and I think our answer as well, was 40, and then the back of the book says 20, so I'm not sure. Okay. Now let me see. We're talking about power. So what is power? Power is the amount of work you can do in a certain time. The more work you can do, a little amount of time, the more powerful something is, So that's how you think of that. And so let me see, what is work? Because we don't really have anything that says work here. Work is what? It's something times something. What is that? Yes. Force times distance. And like I say, this might not always work, but it's worth a shot if you have, if you're unsure of if you have no other ideas. So we've got time here. And then, let's see. Let me break up what force is. So I'm going to do this way. I'm going to take my expression here and plug, for force and just plug it in here. So we've got, I'll say distance. Let me see. Force times distance over time. Okay. And as it turns out, distance over time is velocity. As over time times, let me see, put it this way. Mm-hmm. And so if you plug in the numbers here, let's see. So we got this part, which is at 10 kilograms over a second, times velocity, which is 2 meters per second. And I squared that. So just looking at the numbers, you got 10 times 4, which equals 40. And that's what it gives you. So that's what we got. Yes.
I think that's a
Okay.
This one, the one you use for the first one,
Mm-hmm.
you use acceleration. Okay, that's normally the main force. And they say that the speed is constant. If the speed is constant, it means it doesn't have an acceleration.
Okay.
So the first part, I think you need to like, because you said the formidable was
How? Say it again.
10.
Yes. Yes. This was 10.
You can go in and have it.
Okay. Let me see. So what do I need to change up here?
Well, you don't need to use this one.
Okay. Let me see. Oh, that's right. Because acceleration would be 0.
0 plus is constant speed.
Okay. Which formula would I use then?
Work done is equal to kinetic energy.
Okay. And hang on. Can you come over here so the audio can hear you? First of all, do you all have any other questions or anything? Tonight I'm having one, and then I don't know what the schedule is for everything else. There is one on Saturday with Mr. Van der Zijden, and then 8 to 11. Yeah. So,
We can turn in the corrections on Monday,
yes, yes,
Those
Yeah.
are for the exam, so
You can correct it for the, even if you pass it.
oh yeah, yeah, on the ones you didn't
Yeah.
do, yeah. So you can earn up to, so where you are in 100, you can get up to halfway to that point.
this is gonna
So,
go as slide.
I think so. So the stuff that he presented yesterday is not, yes, it's not. So,
So the corrections are due by the 30th, right?
By Monday.
yes, let me see.
That's what you said you're gonna extend it
Our
to the
exam is
30th.
next Monday.
Let me see, because your exam, yeah, for the third. Okay, so not this next Monday, but the Monday after that, to give you time to just kind of relax a little after the exam and have a week to work on them, and then it'll be due. Yes, yeah, I need them so I can just kind of look over them.
What about, I have one of the exercises that says, these guys are checked out, and I don't have any mistake, there's any kind of one with this. But she checked it out, she told me there's nothing that I can correct.
Okay, okay, let's check in on that.
The second exam's gonna pull off of this type of work that we're looking over right now.
Yes, it's type, yeah. It's hard to kind of say, I mean, I'm just kind of going over problems, but it's hard to say whether or not I'm, preparing you well. I'm trying to be as, comprehensive as possible, or as detailed, I guess, as possible. But just try to practice as many different problems as you can on your own. So just kind of get really comfortable with the formulas. Okay. Do you have time to stay behind a little bit?
Yeah, I don't have the time with me right now,
Oh, okay, okay,
so I have to be here.
okay. Do you want to meet me in my office at some point, or later next week or something?
I can just think of like, next class is fine.
Okay.
After the test, I can just show you.
Okay,
I mean, if there is something I can, if there's any correction, that's fine, I can do it. The thing is, it's best to check it out, and she didn't see anything.
okay,
So I don't know exactly what I'm missing or what can I do to this.
okay. Okay, well, yeah, let's definitely revisit about that. Did somebody else have a question? Okay, so,
I think they used last Saturday, the doctor was in the study session.
mhm.
He used a different form. He used power for it. Right. That's what I want to do. He used power and he used work, right? Yes. Because he used when you get a difference of kinetic energy is equal to work done or the work net work. And then from then you know that the rate of mass is changing. He uses the derivative for it. Yeah. And then you get a 2. That's why it's 10 and 20.
Okay, let me see, hang on. Do you have a question that
No, I was just gonna tell you, I'm not here on the 23rd.
Okay.
For the exam, so will there be a chance to do it
Um,
after?
yeah, let me visit with Dr. Bolton to see about making up, because there's another person I need to.
Yeah, I have my NASA internship that entire week.
Oh, wow, okay. Well, good luck to you on that. Where are you going?
To Mississippi.
Oh, okay, cool. Okay.
Just let me know. Thank you.
Mm-hmm. Okay. All right, so you say work is what we really need to look at, correct? Do you want to write it on here? Are you comfortable with that?
Just like. Oh, thank you. So we have a work done.
Oh, click right there, the
This is
pencil
the
icon,
pencil.
yeah. And it's in black, and then you can choose which color you want.
Fine, black. So we have work done is equals to kinetic energy. So just equals to half mv squared. So from there we have, you know, squared. So if you take derivative,
Derivative of that. You take the derivative one time. So if you divide the derivative, apply the derivative on one side and the other side.
all right.
To get power, okay.
So you get derivative over dt. And then you know the velocity is the same, it's constant.
Right, that's why you done.
Yeah. And that's the change of rate, which is state. That's what you get it to from kinetic energy. But also you know that this right here, this is power. And
Yes.
power is force times velocity. So from force times velocity, you equal to that, and you can cancel velocity. Velocity on this side, one velocity on this side. You still got mass, force, and one velocity only there. The power is force times velocity. Yeah.
Yeah, you did that then. So
What is it?
you did it. You also did it. Like when you had it, it was equal.
Oh, okay, when I went through that whole, okay.
Power is equal to, that's power right there.
Right.
That's force times velocity. So when you equal the two powers, you cancel one b, and you get 10. So then I guess they apply the derivative because you're talking about the rate of change of mass.
Okay.
So in that case,
So just be on the lookout for those terms.
yeah,
Okay.
I think they use impulse there for that. I'm not sure about that.
Also impulse, yeah, I need to write what that is.
FV. Impulse, right?
FV?
Mhm. Oh, is it FV?
No, it's
FT. Sorry, FT.
momentum.
Oh, change in momentum.
Momentum, yeah, change in momentum. So when you cancel the V's, then you got the force there, right? You got the force 1/2. The change of rate of mass is 10, and the velocity is 2. And then the 2 and 2 go, and then the answer is 10.
Wonderful.
Oh. Okay.
The teacher on last Saturday, he did it
Okay.
this way. But he went too fast, and I asked him the second time, and I couldn't catch up.
Okay.
He was working on different groups, doing
Oh,
different.
okay.
It was just 3 of us for this class. I think it was, I guess, for 2 or 3 more classes. Even people from other rooms come over here.
Okay.
And I was, oh man, that when I saw the derivative, I'm thinking, and then on the problem it said the rate, that's mass over time.
Mhm.
So that's why they use the derivative. And then I put everything together over the weekend.
Okay. All right. Yeah, I think he has several different groups because he's here on Saturdays because he does the like the remedial classes. They have a like workshop type deal in there, so he's going to different groups and helping. So
How do you move it? Or should I write here?
that's good.
Okay.
That's
And then
all-
it continues to what you've done, but just change the sign. The
Yeah, I think
I'll be
so.
here.
Let's see.
I'll be here the next Saturday. This Saturday.
we have
Okay. Do you think you'll make this evening? I mean, no pressure or anything, because I don't know what we'll go over this evening.
Yeah, we do all the homework, right?
Yeah, I might
Are
do
you
more.
gonna bring some new problems or?
Well, not I didn't go over
I
the,
don't think I can make it this
okay. Well, that's fine, because I didn't go over at least two of the problems in that last week's PowerPoint thing. I might work on those.
Well, he was saying that we study PowerPoint, right, for this test study. He was saying go over the Dr. Rush, right?
Oh, yeah.
He was saying he said study the problems from the PowerPoint.
Okay,
So I just,
okay.
I think that's all.
there's a lot of problems there. I need to print it out and go over again. And also some of the guys from the class, they went to some website and they put the answer.
Oh, okay. Like
I think it's check or something.
okay, I think that's familiar.
Yeah.
I don't really know how that works.
They got this answer, but they couldn't. They don't explain you how.
Yeah.
But when I saw the name rate over there, the rate of mass, and the velocity is constant, so then you can apply the derivative. It's the rate of change.
Well, thank you all. I mean, like I say, I'm learning as you show me things. I'm kind of learning as you all learn.
Really,
so
when I
this-
saw this one, it threw me off a little bit because this is word net. This is the word down net.
Okay.
But in terms of velocity, there is going to be initial velocity and final velocity. But in this case, the velocity is constant. So the only thing that is changing is the mass, which is the weight.
Right.
Okay. See, yeah, that's so easy to miss. Well, okay, it's easy for me to miss. Well, I missed it. I'll put it that way. I missed it. So
And then is that key that power equals to force times velocity. That it helped you a lot to solve the problem right here when you equal the two. You cancel the two V's. One B square and the other B on the other side. So they.
thanks, Ken. This is well put. Do you mean here when you, well, hang on. When you, do you mean kinetic energy?
Yeah.
Okay. All right. Let's see.
That should be differential.
Changing kinetic energy.
Yeah, that's differential.
How do I put that?
That should be the differential. Like
Oh, dx. Let me see.
that's the triangle.
Oh, okay.
That's according to.
Okay.
Yeah, but you know from the problem that the velocity is constant.
Yeah.
So the only thing that is changing is the mass. It tell you over there over the time.
Okay.
That's why you apply the derivative.
Actually, hang on. I don't. That looks confusing. Let me write.
And if you want,
Well, I gotta go. Thank you, sir.
Okay. Well, thank you.
I don't think I'm gonna be here this afternoon. Yeah.
Okay. I mean, no pressure. Don't worry about it. So, I'll be here regardless.
Are you gonna record it? What are you gonna do tonight?
Probably so, because this is pretty easy. So,
So you're gonna bring some more problems, like
I want to.
from the PowerPoints or something.
Yeah, I want to, because there were only, I think, 2 problems I got to of the 5 that I was given. So I still need to go over those in a separate PowerPoint that he gave me for those problems that we went over last week. So I can go over the rest of those.
From the homework, or is a different set of problems?
Yeah, it's a different set that he sends me. So for Wednesday, he sends me worked out problems. And so that's what I present on.
For this one.
Well, not for this one, actually. He didn't send me any problems this time, but last week he sent me an actual PowerPoint that I used to write up here,
So you're saying you got a new set of problems for this afternoon?
Yes. Yeah. So,
How many? Like 5?
well, just 3, because I already went over 2 last week. So,
Okay.
so yeah. And then I think there's some more in the.
But you're gonna put it on or black and white, as a video or something?
Yeah, or just email you the link, hopefully.
Okay, yeah.
Upload it on YouTube.
Because I've been working on the homework
Okay,
and then all the theory,
okay.
but I didn't look the PowerPoint so much.
Okay, and see, neither did I,
Yeah.
so this will give
And
me
then I
time to
saw
do that.
one thing that I noticed is he was talking about the problems of the PowerPoint, and the whole work is talking about energy, power, velocity. Yeah, but he don't put anything on the PowerPoint. The whole work
I think
about momentum, nothing about momentum.
Okay. There is a problem that is about momentum. It's
What?
about like change in,
On homework?
on the PowerPoint thing that I'll,
Oh yeah,
Go for
on the PowerPoint, yeah.
Yeah.
But for the homework, he didn't put anyone. Yeah, bro, it's gonna be there.
and I didn't see something like power on the PowerPoint.
And then momentum, you got linear momentum on one dimension, 2 dimensions. So you gotta take care about that.
okay. Well, in the one I
he's
have,
gonna come out with one on the test.
yeah, so,
He's probably gonna put one on the test. Yeah.
all right. So we'll save that. Okay, well, let me go ahead and stop the recording.
Oh, was you recording?
Yes, oh yeah, sorry, I got all of that.